Hi, so today we're going to talk about our new unit, thermal physics. Also, I'm going to call this thermodynamics. So here, when we're talking about thermodynamics, we have thermal, meaning relating to heat, and dynamics, the study of how forces affect objects. So it's going to be kind of the overarching idea of our next unit. But first, we're going to talk about temperature and thermal expansion. So temperature is going to be a concept that will develop a little bit in more detail later on this unit, where thermal expansion is a topic that's one of those things that's fair game for the AP exam, may or may not be on there, so we'll talk about it just in case. Alright, temperature. So colloquially, we would say that temperature is how hot or cold something feels, right? But this is a pretty ambiguous definition, scientifically speaking. A little bit more in a hands-on way, temperature is what a thermometer measures, right? This is a better definition, scientifically speaking, but just saying how something is done doesn't necessarily define it. So we're going to define temperature again later on in terms of kinetic energy. But for the time being, we'll say temperature is what a thermometer is going to measure. Now, I just want to mention here a common misconception. All right. So let's suppose you go outdoors in winter and you compare the temperatures of the wooden porch and the metal door frame. What do you notice? All right. So you might notice that when you touch the metal door frame, it feels, so to speak, colder than the wooden porch, right? But this is incorrect. They're both actually the same temperature, right? They're both out in the freezing cold in equilibrium in temperature. So they're the same temperature. The difference is that the metal is much better at taking heat away from your hand than the other. And we'll get into this later on as well. This is called conduction. But I just want to mention that here, right? So just be careful with that common misconception. Things can be the same temperature, but heat conduction can be at a different rate, so it makes it makes your brain think that something's colder than the other, but it's not. So when it comes to temperature, we're going to use various temperature scales, right? So you can kind of think of this is what a thermometer is going to read. Actually, thermometers are a pretty interesting thing. But I don't want to get into it. But basically, the temperature scales that are typically used in everyday life are created in such a way that boiling points at a certain value and freezing points at another for water atmospheric pressure. If you want to learn a little bit more about the history of Fahrenheit, I linked to something here in the PowerPoint you can find online. But basically, Celsius defines the freezing point of water to be 0 degrees and boiling point to be 100 degrees Celsius. So when you talk about those degrees, it's degrees Celsius. Whereas Fahrenheit, freezing is 32 and boiling point is 212 degrees Fahrenheit. Now, Kelvin is our SI unit for temperature. So for the most part, we're going to be using temperature in the units of Kelvin. All right. For Kelvin, it's basically scaled, it's a scale that's defined where absolute 0 is a value of 0 Kelvin. So absolute 0 means that there's 0 molecular motion, so we'll talk about this later, but that means 0 kinetic energy. So basically that's non-existent. There's scientific experiments trying to get to that point, but nonetheless. Just be careful here. This is not degrees Kelvin. That is not a thing. It's just straight up Kelvin. All right, so freezing point of water is 273.15 and boiling point is 373.15. So basically you're taking Celsius and scaling it up. I just want to quickly mention here, you can convert from Kelvin to Celsius by adding 273.15. You're not going to have to convert from degrees Celsius to degrees Fahrenheit. If you do, you can just simply Google what that is. but this would be the one thing that you would have to perhaps memorize for the AP exam in case you need it. Some typical temperature ranges for the universe. So why am I mentioning this, right? So a lot of times when we get to an answer, we want to see if it seems reasonable. So here's an idea of what answers you get might be reasonable. So human survival is a very small range of temperatures, right? So it's about 75 degrees Fahrenheit to 111 degrees Fahrenheit, where our body temperature is 98.6, and I have the Celsius relations there. The lowest temperature ever recorded in a lab experiment, at least this was as a couple of years ago. This might have changed, so sorry if this is old news. But there was an experiment conducted in Helsinki that got to a value of 1 times 10 to the negative 10 Kelvin. Coldest temperature, natural temperature recorded on Earth is 184 Kelvin. And then the coldest place in the known universe is 1 Kelvin. All right, so kind of some temperature ranges here. Oh, let me delete that. Click to add title. And click to add text. Sorry about that. I meant to do that before I hit record. So here's a temperature scale in Kelvin, just to kind of give you an idea of some relative temperature ranges, and I thought it'd be kind of interesting for you to see. All right, so let's talk about thermal equilibrium. I already threw that kind of word out earlier, roughly speaking. So thermometers actually measure their own temperature. All right, their reading reads what the temperature thermometer is. So how can we say that they measure the temperature of their surroundings? Right. So any two systems that are placed in thermal contact, and what that means is that heat can transfer between the two objects, they will eventually reach the same temperature. All right. So you probably remember from chemistry class, but where heat transfer and thermal contact is going to be where heat flows from the hotter object to the cooler object until they're the same temperature. All right. So then this is called thermal equilibrium, and no further changes are going to occur. So this leads to something called the Xeroth Law of thermodynamics. All right, we're actually going to have a couple more laws of thermodynamics. Here's kind of, I'm assuming this was kind of tacked on after the fact, and then they put it, and it's so fundamental they called it the Xeroth Law. So this states if two systems, A and B, are in thermal equilibrium with each other, and then B is in thermal equilibrium with C, then A and C have to be in thermal equilibrium with each other. All right, so kind of like in math class, ooh, I don't remember the name of it. I'm not even going to bother looking it up. But if A equals B, B equals C, then A equals C. Basically that idea. So, a question for you. Does the temperature of an object depend on its size? So the answer here is no. The system, we can basically, if we have an object, we'll call that our system, and we divide it into smaller parts. They're all in thermal contact with each other, right? So they're all going to be in thermal equilibrium with each other. So when we say that, so this says that temperature is an intensive quantity, right? So intensive quantities are quantities that are independent of size. Oh no. Oh, I forgot I wrote this all in the next slide. All right. So what are some other intensive quantities that we've learned about? All right. So I next want to talk about thermal expansion. So thermal expansion is the change in size or volume of a given mass with temperature. All right. So solids, liquids, and gases can all expand thermally. Thermal expansion is what's going to drive some natural heat transfer, whether that be like heat rising in your home, so that'd be why your attic in the winter is warmer than your basement, or ocean and its currents, or even just weather pattern systems. These all are kind of dictated by thermal things, thermal expansion, really. I Actually, I thought I had a picture of this. I don't know why I don't have it on here. All right, fixed. So here is a railway joint. So you see here that on the railway, there's these gaps, right? So the reason why these gaps are built in is because when the railway heats up, so maybe in the summertime, the metal will actually expand. And then in the wintertime, it contracts. So this basically gives the material leeway so it doesn't crack and break and cause a fault. So a question for you. Why do you think hot air rises? I recommend you explain this or attempt to explain this in terms of things we've talked about last unit. So in terms of fluid dynamics, right? Because here air is a fluid. So think about what's going on with thermal expansion, density, and buoyancy. So hot air rises because there is an increase in volume, right? So when air heats up, it's going to expand, which means that the density is going to be smaller than the density of the surrounding air, right? So the object decreases its density, it's going to cause a buoyant force on the hot air upward. So that's why hot air rises. Some basic properties of thermal expansion are that it's related to temperature change. So the larger the temperature change, the larger the expansion. And secondly, it does depend on the type of material as well. So the thermal expansion of alcohol is going to be much greater than the expansion of, let's say, glass. So maybe the glass container surrounding it. So if we look at kind of the microscopic rather than the macroscopic cause of thermal expansion, microscopically, we've got these atoms of the material kind of, moving around, right? They've got some amount of energy. You learn from chemistry class that atoms are kind of always in motion, some more than others, right? Especially in gases. Now, when these atoms and molecules are vibrating, right, they're pushing against each other, exerting forces on each other, right? So when you're heating something up, then these molecules are going to actually increase their vibration. We'll actually relate this a little bit more rigorously to kinetic energy later this unit. But basically, we have an overall net effect of these pushing forces causing the molecules to be pushed further and further distances, right? It's applying more work on these, on the neighboring atoms and molecules, right? So then on average, this adds up to a larger scale for the whole body of the material. If you want a formula, here's a formula. It's not on your formula sheet, so I don't expect you need to use it on the AP exam, but I'll mention it just in case. So this is for linear thermal expansion. So this would be assuming that we have some one-dimensional amount of material. So just kind of think of that as like an infinitely thin string of material. A lot of times we can approximate materials in this way. So for example, those railway joints, well, we can approximate those as being one-dimensional, even though they're not. They're actually three-dimensional. So here, if we analyze the change in length, it's going to be directly proportional to the original length of the material, the temperature change, and then this value alpha, which is a coefficient of linear expansion. So it's a proportionality constant that varies slightly with temperature. So we've got kind of, it's a more complex relationship than this, just kind of what's depicted in this formula, but there you go. All right, let's see. This will give a good spot to pause and for you to start the next video.